Okay. Um, today's lecture, I'm going to build on the lecture from last time, but go into a lot more detail on motivations for scalable software engineering and system in data science. And I'm further going to, as time allows, explore some of the tools that we'll be using in the course of this class. During our last lecture, I had done two broad things. Number one, I characterized some of the expectations for the class, which I noted would be highly interactive, and we're going to start that interaction today. This course is going to involve central use of several tools for solving problems together, and those tools include a package called Apache Zeppelin, a large-scale data science tool called Spark, a NoSQL database called Cassandra, and a set of specific adaptations of Spark to other tools such as through Apache Bahir for social media mining. Okay, we're going to be in today's lecture starting to look at the first of those tools, Zeppelin, and the second as well in the form of Apache Spark. Okay. So that was one focus last time. The other thing that I started to talk about last time was the need for supporting data science using scalable software engineering. And within this context, okay, why isn't this opening? Let's just go close that. Within this context, we're going to specifically be discussing a set of concrete motivators for scalable software engineering in data science as it relates to this class. We noted that the area of data science, or the sort of discipline of data science, seeks to provide a set of tools, technologies, and concepts to produce systems to secure data, insight from data. And this includes a wide variety of supporting mechanisms, including software systems like Spark, Hadoop, large-scale systems for high performance data storage and data manipulation, and then methodologies and procedures for using that data, for leveraging that data effectively. Much of data science is focused on making use of big data, and I had talked a little bit about some aspects of this big data. I had noted that when it comes to this class, we have a particular application interest, although not exclusive, in health-related big data, data related to human behavior. And in this area, we have a big data ranging, say, from mobile data collection with apps on the one hand, on the more detailed side, which might give, in some cases, hundreds or thousands of measurements per second for things like accelerometers and gyroscopes, down to less detailed but still voluminous things like Twitter monitoring, where we have, from Saskatchewan, tweets arriving every few seconds, to search monitoring, where we might have data summarized at the level of a day. But what all of this data has in common is what's sometimes called as the 4 V's. And this is a term that was introduced by Google to describe elements of big data. And I think it's the most effective operational definition I know about. The four V's are volume, that's the big in big data, velocity, the data is arriving quickly and over time, variety, so we're collecting at any given point from the same user and for the same period of time. We often have many types of information arriving. So we have tweets that they've been exposed to, perhaps where they are as measured by GPS and Wi-Fi. We might have some sense of who they're with using Bluetooth or Bluetooth low energy. We might further have some sense of their physical activity levels recently through accelerometry, and potentially something about what they've recently browsed to through instrumentation of their browsing interfaces. So that's variety. It relates to the same user, same period of time. We have a bunch of different lines of evidence for what's going on. Now this is important because each of those lines of evidence brings different information to the table. And sometimes for the same point of interest, we have evidence from multiple lines. So if we want to know who they're with, we have some evidence from Bluetooth, perhaps, who's nearby, but we might also have some evidence from where they are. For example, if I'm in this class at this time, my phone might detect a few of you and a certain dog via Bluetooth protocols, but we might be able to infer reliably that I'm probably with a set of you and who that set is by knowing something that this is class time and these people are in the class. So location often tells us a lot about who we're with. If I'm teaching my undergrad course in the afternoon, we know a lot about who I'm likely to be with. Similarly, if we want to know, for example, am I taking a smoke? Am I smoking right now? We'll have a sense of that, not only knowing where I am, like if I go outside when it's minus 30 and I'm sitting outside, there's a pretty good chance that, and I come back in directly and I don't go anywhere outside other than just outside the building, I'm there for about 10 minutes. The chance is pretty good from location alone that I am smoking. But if you also consider who I'm with, and I'm with another smoker, the chance goes up some. If we consider the fact that I'm kind of pacing around or sitting, that might clue us in a little bit more. If we have a Fitbit or Xiaomi around my wrist, and we recognize the fact that I'm making rhythmic movements towards my face, the chance that I'm smoking goes up yet further. So the point is that often when we have variety, we can get this ability to triangulate, to kind of get a sense of what's going on from multiple angles. And we may have a single concern. Am I smoking? Am I driving? Am I engaged in sedentary behavior? Am I sleeping? Am I standing or sitting? But it's multiple lines of evidence that we use to determine it. And we're going to see a lot of our focus in this class is in linking up lines of evidence, multiple lines at the same time, same user for that sort of insight. Okay. Another component that people sometimes say characterizes big data is veracity. And the issue here is a combination of two factors. One thing is that it's been shown for decades that people have very poor ability to reliably report on certain areas of knowledge. Let me give a few examples. People tend to be pretty poor at reporting what they eat. If you ask someone every 3 months what they've eaten for the past 3 months, people's estimates of that are not very accurate. We know this from large-scale health surveys, comparing them with validated measurements. And we're not that accurate. If you ask how much physical activity did you get, people are also not that accurate. And it's not necessarily because they want to confabulate. It's the fact they have a hard time remembering. What stands out when they ask how physically active you've been? Maybe what stands out in their mind is, I played hockey last week. I was out skating a few days ago, and they know from the point of view of an interviewer also, it's kind of nice if I say I'm more active. And maybe they think, well, okay, I bike every day to work. And they overlook the fact that actually I haven't been able to bike for a few days. And so they give an answer that's often quite crude. It turns out it's very, very broad uncertainties associated with it. And for a lot of human health behaviors, this is a big issue. Even with things like location, even things like who they're spending time with. Our own research has suggested big discrepancies between what they report and what actually is the case. Yeah, there's a bit of flakiness here. Certain of these measurements we get from some of these big data sources, these electronic data sources, can help reduce that vulnerability of people, that weakness of people. For example, we can measure with GPS or Wi-Fi how far I am from that Wi-Fi router or that one. I could figure out probably where I am pretty well. If we have accelerometry data from a watch or some other thing mounted at a known location on a body, we can often get a pretty good understanding of physical activity. If we have Bluetooth and we know the other participants are carrying Bluetooth, or the dog is carrying a Bluetooth collar, we know something about with greater reliability who they're with than if we relied solely on self-report. Nutrition. If we don't ask them to report so much as to take a photo of every meal they eat, we know something about what they're eating with greater reliability than they're likely to report it. Partly it's because the reporting is so burdensome, and partly it's because it's hard for them to remember. But with a lot of cases, we can do better. But the other component is this triangulation thing. It's the fact that when we have multiple lines of evidence, any one line may be of questionable provenance, but once we combine them together, the picture is very clear. Okay. So I've talked about each of these. I don't think I'll go into a lot more detail, except to say that in our class we'll be seeing a lot of examples of each of these. I will further tell you that these four things, the volume, the variety, the velocity, and aspects of the veracity. I don't have veracity slides. Okay. That all of those turn out to make it a natural marriage with something else you've heard me talk about, maybe more than you'd like, which is dynamic modeling. Dynamic modeling is something where we often, within a given model, we have variety. We have multiple pathways to effect. We have an interest in velocity because we're modeling over time. We're modeling change over time, and that lines up very directly with this. We're interested in things which have greater veracity to inform that model and to compare with that model. And, models also have a lot of volume associated with them in terms of different lines of output and voluminous voluminous data that they can produce that we can compare with data from empirical evidence that falls into the big data space. So these four V's, it turns out, make big data a very nice fit for informing, being compared with, and having methods that use big data be tested by dynamic models. We won't spend a lot of time in this class talking about that, but some of you may pursue projects that draw on that. Okay? Great. These do preview a few of the forms we'll be looking at. We'll be looking at search volumes for different types of data and harvesting them with Spark. We'll be looking at Twitter data quite a lot in the course of the semester, and looking at the large repository of Twitter data that we've accumulated here over more than the past year for multiple provinces here in Canada, which consists of, by this point, tens of millions of tweets. Probably not so long from now, hundreds of millions of tweets. And then we'll be grappling with high volume. Much of this semester we'll be dealing with tools that are designed to work effectively with high volume data sources. Okay. So in this area, why do we need scalability? Why are we concerned about this thing in the title of scalability? Well, at its most basic level, we're dealing with a ton of data but limited resources. We have limited amounts of CPU speed, of network bandwidth, and of memory to go around. And if we have tons of data, it puts real pressures on what we can do with that. We have limited CPU capacity and we have to use it judiciously. Our networks can get congested and saturated, and we want to use them effectively. And perhaps most notably, memory, it turns out, is a valuable resource. Going to disk, hitting disk compared to hitting memory, drawing, in other words, data from memory rather than from disk, there's orders of magnitude, many orders of magnitude of difference in speed. If we can read something in memory, it may be 100,000 times faster than getting it from disk. So if we can optimize our memory, we can, in our use of memory, we can often gain huge benefits in terms of performance, in terms of throughput, how many requests we can process for a given unit of time, or in terms of latency for dealing with a certain request, we can deal with it much sooner. Another realization that I mentioned last time is that in light of Moore's law, opportunities for increased speed come from using many computational resources judiciously rather than speeding up our processors directly. For many decades, we benefited from Moore's law, that every roughly 1.5 years, there'd be an approximate doubling of the number of transistors on a chip. And that led to a similar, but not identically the same, increase in the speed of those processors and what we could accomplish within a given amount of time. In terms, we could execute the same instructions for the 386 10 times faster than for the 8086. And the Pentium could execute it 4 times faster than the 386. And for many years we had this kind of successive doubling over successive patterns of certain number of years apart. And it was amazing. It was log linear. In other words, no matter how far out you went for those period of years, if you for every 2 years you double the speed of the processor or what have you in terms of accomplishing things. So it was amazing. And I wore a young man's shoes during that time, and I benefited from it a lot. But now, ladies and gentlemen, I no longer wear a young man's shoes. And our life is much tougher in a way because we're eking out speed improvements not from just raw doubling of our computational speed by our processors every few years. We have to come up with new paradigms, new ways of coordinating the efforts of many independent units, because to the degree that we're increasing transistor counts per chip, it's no longer directly translated to speed so much as having multiple cores on a chip, for example. So you might have 16 cores on a given chip, or 16 logical cores, or 32. Or we have GPUs out there. They stand before us. And we might have thousands of specialized slave processors on a GPU. But the process of programming them is different than when I was a young man, when life was simpler. And we have to harness these effectively. Much of this course is about how do we effectively, transparently, and concisely leverage the strength of massive number of processors and cores in a fashion that's memory sipping, that only uses a bit of memory, so it doesn't bog down and just accessing disk to solve big problems. Okay, we need to scale up our ability to handle this data so that we can handle very large volumes of data in a fashion that's rapid and that doesn't overwhelm our computational resources from a point of memory and disk, say. But we need to do it in a way that we can program effectively. And the techniques we'll be learning in this class do that. And that's their beauty and that's their power. And at the same time, I argued last time that manipulating lots of data is not merely about the typical case where the data is processed in a reliable fashion faster. Processing vast volumes of data requires us to maturely handle exceptional situations. By exceptional situations, I'm talking about situations where the data is bad, where things don't work right. I'm going to make sure that the recording is going fine for this guy. Yes, it is. Okay, happy. So we need to be able to handle failures across machines maturely, not as ad hoc circumstances, but as things that are expected. And we need to have robust mechanisms for continuing on our computations despite those failures. And at the same time, we need to be able to deal with missing values, data where we expected data, but it's absent. It's not present. Or where there's outliers in data, which are aberrations. And we'll see with GPS data, we get this a lot. Occasionally we'll see GPS measurements that place me in Indonesia or place me off the coast of Nigeria. And then, the next second, it'll recognize I'm back here in Saskatoon. And, I know you folks think I travel a lot, but I'm not going that far. And not that quick. In fact, it might even violate, it would require relativistic speeds potentially. And so the fact is we have to be able to deal with these outliers in a reliable fashion, in a routine fashion, not as ad hoc occurrences that require special human care for each of them. We don't have that luxury if we have 100 gigabytes of data that we're analyzing. And similarly, we need to deal with error conditions in processing, divide by zeros, etc., because chances are we'll get situations which are not typical, but which are frequent enough in large data, we have to just be able to handle them as a matter of routine benefit. So we need to have software that will allow us to build pipelines that will be concise, clear, at the same time able to handle all these exceptional circumstances. We don't want to litter our code with tons of exception handling, which requires very complicated reasoning to reason about what happens in the case of the exception. So the other thing, though, that's a big issue here is data science involves, as a discipline, being able to go from, on the one hand, exploratory type of analysis, where we're pursuing broad strokes, kind of getting to know the data, what's there, what are the broad patterns in it, where are the clusters, what trends do we see, what's the quality of this data. We often engage in that type of behavior, and we want to do high-level queries very quickly to learn from the data. But then we want to also put into place mechanisms which are routinized, where the data that is collected can be routinely used for insight. A classic example of this that Ujie and Bopu are dealing with down at the police station. We might have analytics, and I think, Whale, you're involved and maybe involved in some of this too. Okay, but others in your group, I think, yes. We want to put into place exploratory mechanisms where we might discover a person who's at risk of domestic violence or a person at risk of suicide. But then we're doing that exploration, evaluation of machine learning algorithms to determine these things. We want quick turnaround and being able to kind of learn what works, what doesn't. But then on the other hand, we want to translate these things so that the social services, Ministry of Social Services, or the police can follow this on a day-by-day basis very routinely without, having a windshield next to them. I thought, wouldn't that be awesome? Wouldn't that be awesome? You could, pay $1 million a year, you have your personal windshield. So, ladies and gentlemen, we want the ability to routinize things at the same time do exploratory work. So the scripting-like interaction interactively, where we want to make quick changes to code base, run commands over large clusters to get fast results, but then we want rigorously tested and validated code bases that work very routinely so we don't have to bother these busy police officers, with the code breaking every 2 days, and they have to call Iman and say, come down here to the station or something. Okay, so why are we focusing on functional programming and Scala? Why are you focusing on Scala, on Spark as a platform here? Well, there's a lot of reasons, and I want to highlight some that have particular relevance here. Scala, as a language, supports this very powerful functional programming paradigm, which when I was a young man was actually the first type of programming I learned in university. My very first semester in university, I was in that first year learning functional programming, and at that point it was a niche area of computer science that people at MIT recognized had incredible power, but the rest of the computing world had largely ignored it. There were in academia people who recognized this is transformative, but it really wasn't widely known. These days, it is seen as an absolutely key technology for data science, and is seen as a key technology for a lot of domains where they've run into problems with traditional purely object-oriented or purely imperative programming techniques. And functional programming provides unique features that address data science. We'll be talking about here in that the first chapter of the book starts to comment on. But I want to highlight some of the ones as it relates to Scala, but bear in mind that some of these have overlapped with the functional programming benefits. So the fact that we have a lot of data and we have limited memory, ladies and gentlemen, we have limited memory on our machines. We may be processing, 100 gigabytes of data, and I have 16 gigabytes of RAM on here or something like that, or maybe processing terabytes of data with 32 gigabytes of RAM. One of the things that this means is we don't have the luxury, as we'll see, of taking data structures for the entire data set and loading them and transforming them to another data structure for the entire data set at a time. We can only look at a piece of the data set at a time. It's like looking at the world through a straw. I'm looking at just this little bit of the data at this little point. And it turns out that it's very non-obvious, and it'll take you a bit of time to grok why it is. But it turns out that this sort of type of computation called lazy computation, this type of data processing, use the term laziness for it in a computational sense, is key for performing operations on data in a way that doesn't require us to process the entire data at once. Okay, it doesn't require us to have large areas of the data loaded at the same time. We can do it in an incremental fashion. We could have a whole pipeline performing things on the data and do one piece of that pipeline transforming a given data item successively, rather than having the whole data structure performing the first operation on it, then the whole data structure performing the second operation, the whole data structure performing the third operation. Turns out laziness is key. Another reason that we get out of this is the ability to recompute with Scala. With Scala, we're doing functional programming, which by and large means we don't have to worry about side effects. So if we have referential transparency. If we have one expression, we can reduce that to a certain value, and wherever we see that expression, we could substitute the value. It would be no change from it. And so if we have that expression again, rather than recomputing it, often we just reuse the value. But with functional programming, we have the opportunity to discard the value. So we don't have space to store this anymore. Just recompute it the next time. So we have the choice whether to recompute or to reuse. And if we're short of memory, we often recompute rather than reuse. And so that allows us to avoid using memory when it's advantageous to do so. It allows us to instead do the computation again because memory is more valuable right now and it will cost more than it's worth to use that memory to store the value. So recomputing, it turns out, is something we get from Scala in addition to laziness. So another thing we get when we have a lot of data to process and we want to use many processors concurrently to handle that often. We want to go and filter this array. Maybe we have an array of data. It has 100 million data items in it. Maybe it's data from Twitter. And we have 100 million tweets. We're going to probably have that soon here from Western Canada between Xiaoyan's, my own, and Anahita's Twitter harvesting. So we have 100 million tweets. We want to filter them to be tweets that mention something about influenza. We could have one processor go through tweet by tweet. Is this tweet about, does it mention influenza? Nah. The next one. Is this one? It turns out that would be pretty expensive to do, and it would take a long time. It would be much more advantageous if we had a machine with many processors on it, many cores. Maybe we have a machine not long from now with 32 cores on it effectively. It would be really nice if we could map that out to those cores and have those cores work on it. And it turns out that this is a lot easier to do when you have clear dependencies in a language. You know what depends on what. And if you have parallel data structures that are optimized for parallelism, and higher order functions that can be applied on this core, on that core, on that core over the data in a way that performs a particular task at issue. So it turns out these are all things that Scala supports very well. It's parallelizable data structures. In Scala, you could simply say this data structure dot par, and that will get you a parallelizable version of that data structure, which then you can farm out to machines in an efficient way. The ability to handle robustly handle exceptional situations, it turns out that once again Scala supports this very well through type checked handling of errors. Rather than just having a return value, -1, that indicates something bad happened, or not a number. You actually have a type safe, a way of indicating that's completely clear and self-documenting that an error occurred and what error occurred, or you have the value, and you know which has occurred, and you can handle each one. You don't have to remember, -1 is not a real index, it indicates a failure occurred, and you don't risk code that will make the mistake. So Scala is a language, reflecting its name. It's the first part of Scalable, and that's why. It's designed to be scalable from data exploration to large-scale rigor, to have really big code bases written that we can have great confidence they're correct because of type safety, because they can be shown to be safe from this perspective of how they handle types. But at the same time, it allows really flexible data exploration with a lot less syntax burden than you see in something like Java. With data exploration, we often have a need for flexibility of processing. And what we really get there is in Scala, and Scala on Spark inherits it, modular pipelines of operation. It has a rich type system supporting subtyping, parameterized types. Very nice. We could say this is a list of X, where X is, a type, right? A hash table from this to this. It has a mix of sort of compiled form. This is a mix of interaction. We have the Scala shell and compiled forms. It is a compiled language, but we can interactively use it, and we will be interactively using it in the context of Apache Zeppelin. But there's also the Scala shell, which you'll occasionally see me using. It is compiled, and what that means is, it's rigorous type checking. We'll be told if we have something that's incorrect in our code base from a type perspective, like we're trying to use a string as if it's double. It'll tell us. It won't wait till runtime. We'll run our code and boom, it blows up. We can have, if we want to have a large-scale data pipeline that's robust, it benefits us to know about as many errors as possible up front. And this can spot a lot of errors. And it's performant. It can offer quite good performance, and that's improving all the time. At the same time, it supports this thing called monadic composition and monads in a way that's utterly beautiful, powerful, much cleaner than other ways of extending, of capturing this functionality, and allows us to have basically the same code and use that code in very flexible ways to accomplish a whole set of different possibilities that can be extended easily. And monadic operations are something we'll be glimpsing as part of the class, and a lot of what makes Scala powerful as a language, and indeed Spark powerful as a platform, is that we leverage monads. Okay, these structures that are like packaged values, self-documenting values that are wrapped up with packaging around them that keep information about the values. And it sounds a bit mysterious, but it turns out you'll get very familiar with some of them. Some of them like stream or option or either, etc. We'll be using in the course of the semester try to indicate cases where we've tried something, we may have a value or we may have an error that resulted from it. It has a quite minimalist syntax. Compared to something like Java, it's just much more compact syntax. And in fact, the way in which you write Scala includes conventions that make it even more compact. Okay, you can leave off parentheses around things that passing them their first argument if that's the only argument they take, etc. There's an interactive interface for exploration, a REPL, a read, eval, print loop, where it'll read what you request, it'll evaluate it, it'll print out the results, and it will loop back to take your next thing. And we'll be using that centrally. We'll get a glimpse of it this time. And it's an extensible language. This is one of the awesome things about Scala. You can really easily build domain-specific languages on top of it. You can build languages that are specific to a certain purpose on top of it, such as a language called Frabjous. Okay. Okay, so let's talk about functional programming, because Scala it's a language that marries functional programming with object-oriented programming. You folks, I'll take it as a given that those in the room are fairly familiar with object-oriented programming and the benefits that it brings, subtyping, subclassing, the hierarchies we build with those. And there's a set of subtleties that I don't have time to go into in class, but which are very important there. The Liskov substitution principle, particular risks of subclassing when compared purely with subtyping, etc. But I'm going to take that as a given I'm glad to talk with anyone about it, but it won't be the focus of this class. This class will focus more on the functional programming side because it's that side that is unfamiliar to most students, that side that has led Scala and a growth more generally in functional interfaces to languages to just bloom in recent years. And it's that which is drawing people as a technique to that people are drawn to apply to data science, not so much the object-oriented side. So what does functional programming give us? Well, if you looked at that first chapter in the book, and if you haven't, I'd ask you make sure you do it in addition to the second chapter for next time. One thing it gives us is equational reasoning. It's interesting. Xiaoyan, who many of you know in my lab. Xiaoyan is not from computer science background. She's from engineering background, reservoir engineering. And her first exposure to a computer science class was this one last year. She was in another class simultaneously, but this is one of her first. And I asked her what she was thinking about Scala. She has a very expressive face, and I could tell in the first bunch of lectures she was puzzled by some things, and trying to understand it. But I asked her, and she said, she really liked Scala. I guess if you compare Java and Scala, because she knows both, or C++, which do you like? She said she likes Scala. I said, why? She said, something, it's almost mathematical or something. And she hit it exactly on the head. It affords itself equational reasoning. And this is a feature of functional programming. When think about an expression in a language. If we, let's go try to see if we could pull up a Scala interpreter here. We'll be having some fun here later. But ladies and gentlemen, we all know, for dealing with expressions, computing values, that's what expressions do. They're these sort of formulas computing values. We could write 5 by itself, and it'll obviously evaluate 2 to itself. But if we write 2 plus 3, hey, come on, 2 plus 3 here, that 2 naturally will always evaluate to 5, and that's because this is a functional expression. It has no side effects. There's no things that it's done to change what's in memory, things that it's done to sort of update a disk, to print out messages in each of these computations. It's just performing something that's side effect free. It's performing something that has not changed the state of the computer. So if I put 2 plus 3 again, it will evaluate to 5. And in fact, anywhere that I see 2 plus 3, you could substitute 5, or anywhere I see 5, I could substitute 2 plus 3. They're interchangeable. Mathematically, these are identical. And that's not the case for places where we have side effects, right? Like if 2 plus 3, if this was something like, don't do this at home. Don't do this at home. But if I said in Java something like I plus 3, that's not functional, right? There's a side effect here. Each time I evaluate this, I get a different answer because in computing it, there's a change. Or even if I did foo plus 3, right? Who knows what foo could be doing? It could be doing horrible things like incrementing I, or it could be going and reading in data from a database and then getting the value and updating the data in the database to indicate there's one less book, of Fire and Fury that can be sold or something like that. So this could be something which modifies databases. It could be printing out a message. In any case, each time I do it, I'm going to have a different result from it. So when we're dealing with a functional language, it's kind of like this. This is mathematically identical to 5, and if we want to store a value like 5, we could do so. But if we thought for one reason or another we want to just recompute it because we don't have enough memory to store the result, we could recompute it later. So this equational reasoning, we could substitute in the expression that determines it for the value or use the value. And that's what you get, ladies and gentlemen, with functional programming. You get this ability to reason equationally about your program. You can have composition of similar mechanisms. You can compose things. You have a function from A to B and a function from B to C, and by putting them together, you get a function from A to C. You compose them. And this is going to be very important for our study of monads, but it's going to be very important for our study of pipelines in this course, and for our study of how you do machine learning in the Spark context using ML. You're going to see that there are these transformers that transform like A to B, another one B to C, and we're going to be able to compose them into a whole pipeline that's going to be A to C. And then we treat that as a unit. And that's a functional unit, which we can compose with other things, and we combine them. So we have these composition of simple mechanisms to yield powerful, higher-level abstractions. It's modular, so we can have the same basic expression and perform different things with it. So I'll show you an example that I don't expect you to immediately follow, but if I were here to get a word stream, so I'm going to create here a word stream from a source. Okay, so here we go, and I'll just go type this in. If any of you wanted to follow along, you'd certainly be welcome to, and just let me know. But basically, I am reading in from a document over the web, and I'm saying this is the text that's used in it, because the text has some accents or what have you, and I'm getting the lines from it. Okay, and then I'm converting them to a stream here. Okay, and what I'm going to do is I'm going to execute this. Okay, and I have a word stream here. Okay, in this word stream, if I look at it and I say, hey, what's in that? Okay, so it's running this. I want to make sure I'm connected because I got to get over to the web here. So here, this word stream will contain the contents of the file, and then I'm going to unknown host. Okay, so maybe I'm not connected. Give me just a second here. Okay, hey, so I seem to be. So give me a second. Here we go. So it was saying tinyurl.com. Okay, so I actually used that to simplify the name because I had a much longer name on Google.Drive. So I don't know if tinyurl is having problems now or what. It seems that it's having issues with tinyurl. Okay, I will try to work this out. But what I get back is a stream of words here, and this stream of words is basically going to allow me to process the data which is within this file in a fashion that allows me to sort of process each component of it successively. Okay, so it is having problems connecting to tinyurl. Give me a second. I would like to work this out just for completeness, and I had done this earlier, but not tested it on the network here. So give me just a sec, and I will go back to the original URL and see if it's an issue with tinyURL or with the original URL. If anyone wants to try this, I'd also welcome comments here. Okay, let's just see if the original URL works. Come on.
For us, it says Zeppelin doesn't know what the source is.
Oh, yeah, you have to, sorry. Thank you very much. What you do need to do is import scala.io.underbar. This will underbar everything in the scala.io library, okay? Once you've done that, it should know what source is, and that should allow you to perform this connection. Okay, so it's saying unknown host here, and this is surprising me. If you could let me know if you get.
Yeah, I think it worked.
I'm getting something like this.
Oh yeah. Okay. Okay. So let me just create a new notebook. I'm wondering if it's because I shifted shifted networks or something like that. Let's just try that and import Scala.io. This is going to import all of the things from there, and then I will go and I'm going to switch back to that notebook here. Oops, not. Sorry.
I think we import the HTML document.
Yeah.
Oh, okay.
Yeah, doc type HTML.
Okay. Yeah, for just this.
Yeah.
Yeah. Yeah. So I'm going to go back here. I'll do this, and okay, I will put this here, and this is not yet a word stream. Actually, this is just a document. I'll break it up into a word stream in a minute. Okay. It's also puzzling. It's actually requiring this much time, but I think what's going on here is it's starting a new Spark interpreter. Okay, so I'll go back, and while this is running, yeah, okay, unknown host. Let me just see if maybe there really is some oh, no. Okay, well, mumble. Yeah, I think there's some sort of network issue which is going on here, which we'll have to come back to. So, in any case, well, actually, sorry, I can do something that doesn't require that. It's just easier to do it this way. So I'll go back, and I will say, right, stream, here we go, stream dot from, let's see. So in this interpreter, you can actually do control dot will actually do autocomplete. And I will say here that I'm going to do a stream computation from 0. And this is going to actually create a stream which will consist of successive elements, successive integers. So if I were to say, for example, from 0, and I were to say take the first 10, and I were to request that, what would happen is it would actually define this and would take the first 10 of them and use that. And then I'd need to actually say, okay, compute them. And here it's actually going to compute it. But more than that, I could say, for example, map. So this is I will say, val my ints, okay? My ints equals this, boom. These are my integers. And I could say my ints.map. And for each int, I'm going to specify what I do. And this is where it gets to this issue of orthogonality, ladies and gentlemen, via higher order functions. So I'm going to demonstrate that. So I can say, for example, for each of these integers, I want to square it. Okay? So I will say I'm going to map each one to its square. Okay? So if each of them is called x, map basically says, okay, for each element of this my ints, I'm going to square that element. So if that element is called x, I'm going to turn it into its cube. Okay, and then I'm going to display those. Okay, and here we have those displayed. Alternatively, I may say, okay, I want to take their cubes, so say take their cubes. I'll multiply it thrice by itself, and here are the cubes, right? So I started with a set of the first 10 integers, and I can turn them into squares by just passing this function. I can turn them into cubes by passing that function. And I could perform square roots on them, or I could for each of them I could add 1 to it, or multiply it by 10. This would be yet another operation I could perform. So when I say it's modular and there's orthogonality, what I mean is I can use the same basic mechanism, but pass different particular functions to process them, and I'll get back quite different results. And really what this draws us to is these differ only in this function that's passed in. But this one function that's passed in makes all the difference in terms of the particulars for the results. So it's modular. It's lazy. Ladies and gentlemen, these operations which we've been using here demonstrate that laziness. This my ints, if I go and I look at my ints, you'll notice that my ints is, could you, pardon me for just a second. Hello? Yes, I'm teaching a class. Why are you calling me? Okay, you must have the wrong number. Odd. They kept on calling me, so I thought, okay, maybe my wife is, out. I know she's out shopping, had an accident or something. So, ladies and gentlemen, my ints here is a stream. It's something called a stream, and a stream is something that doesn't have to be computed unless you request that it be computed. So let's define another one of these. Okay, so these my ints here, I'm going to have, forgive the lack of imagination, my ints 2. Okay, and in this case, I'm going to take the first 1,000 ints. Okay, we're going to take the first 1,000 of them. Now you'll notice if I say my ints 2 here, you'll notice that it just tells me stream of 0, comma, question mark. Yeah. So what this is telling me is the first element is 0. It doesn't know what the rest of the elements are, but it knows how to compute them if I need them. So watch this. My ints dot take 3. I'll take the first 3. Okay. And I want to see them. I actually want it to compute them. If I say take 3, you'll notice that it'll take them, but it hasn't computed them yet because I haven't needed them. I've just said take the first 3. But if so this will be a stream of length 3. Yeah.
Can you scroll up? When you said int from 0 to 10,
Yeah.
was it the same? So you didn't know?
Sorry? Oh yeah, it was this. Yeah, it was the same here. Yeah, yeah.
So it only knows the first element?
It only knows the first element here, but it knows how to compute the rest when I want it.
Oh.
So if I say, okay, take the first three, it will say, I'll give you a stream of n's, of 3 n's, but you still haven't asked me for them, so I'm still, all I know is the first, right? So I'm going to ask, well, for those 3 n's, compute them now. Force them to be commuted. This is what this force is. You may think, that, what does this have to do with Spark? This has a lot to do with Spark. We have the same basic mechanisms in Spark. So we'll see this. This is a common thing. Let's look at this. Take 3, force. Okay, now it's showing them to me. It's showing them to me because I told it, compute them, right? But let's try this some more. Now I'm going to say my n's 2, right? My n's 2 here. Ladies and gentlemen, look at that. Now it's 0, 1, 2, question mark. What's going on? Why does it know the first 2?
Is it already computed?
It already computed them. We forced it to tell us the first 2. So it says, okay, yeah, I already know these. The rest, I don't know yet. Watch this. My n's 2 dot. Now, you should be wondering, isn't this kind of weird? I mean, these are all ints here from 0 higher. I mean, this is a very large set. This is a set of unbounded size. But I'm going to say my ints 2 dot map. I'm going to square each one, right? Okay, I'm going to square each one. What's that going to give me back? What do you think? What do you think it'll give me back? Well, it'll be a stream. What will the first few elements of the stream be? Well, it computes only the first one. I'm going to say take the first 10 of them, right? That will give me a set of tenants, and I'll say force them. I want to see them, right? And here they are. Those are the first 10. But this whole set was basically ready. It was representing the operation of the square of all n's. I only asked it for the first 10, so it computed them and obliged. But it's only obliging as much as I need them. Okay. Alternatively, I can say, map this. I could say I want to find of all the squares. Find. We'll do find. I'll do control dot here, right? Okay, come on. Find. Okay. So why is it okay? Find. Okay. No, it should have. It should have at least a filter. Yeah, but there should be a find first, I thought. That's I may misremember the name where this is some n where n is greater than or equal to 1,000 or something like that. We'll see if that it's not find first. It's there's a name which I'm forgetting here, but yes, I could filter all of these that such that n will take n. They satisfy this this criteria. So any that are less than or where n mod 2 is equal to 0. What would those be? What
That with numbers?
Sorry?
That with numbers?
So these are even numbers. Okay. And now I could say, well, take the first 10 of those, right? And I could take a look at those. Okay. So I could force the first 10 of those. So these are the first 10 evens. All right. the first 10 even squares. Right? So these are all ints from 0 and higher. And then I'm saying for each of them compute the squares. And then filter out those that are odd, or only include those that are even. That's what this is. And then take the first 10 of those and show them to me. Right? So here we have a demonstration of laziness. If we were to go here and go look at, and we'd have to be careful here because this is creating a stream which is different from my ints. But essentially, in this, it's only computed the first 10. It hasn't computed the rest yet because we haven't needed them yet. If we wanted to do so, it could compute more of them. Okay, so
I have a question.
yes.
But you said don't try it at home. What side effect is that?
There are certain things you want to be cautious about trying at home with streams, because streams commonly describe boundless computations, okay? And there are some things that I can do with a stream that will not return. So, for example, I could ask the stream of squares, find me the first which is less than -1. And it will keep on looking. It's not smart enough to realize, there's none. So it will keep on looking for me. And I'll say, force it, show it to me. And it will just look and look and look and look. But no, you could work with them and hope. Just recognize that sometimes, it may not return because it's a potentially boundless computation. So it supports laziness. It supports this idea of only computing when we need it. And it turns out this is absolutely central to the value delivered. It's not just a nice feature. It turns out to be really central, and it supports 3 or 4 different forms of laziness. Scala does, and Scala and Spark. 3 or 4 different types of laziness. Something called call by name, streams, which we've seen a little bit of. It also supports something called lazy variables, which serve a very useful role as well. Now, there's more transparent error handling as well. So it turns out that within Scala, we can very neatly catch errors. So we saw earlier there was an error that was not caught, right? And I'm going to turn, ladies and gentlemen, I'm going to turn lemon into lemonade here. So here's an error, ladies and gentlemen. Here's an error in all of its glory, right? And what I'm going to do is to import. I'm gonna wrap this around. Wrap around this a thing called a try expression. Now, I'm trying to remember. Scala try is actually, I think you need to import from Scala collections. Would you mind looking that up, Dorian? Scala, I think it may be in the collections library. I'll just try creating it here, but I'm pretty sure you have to import it. Yeah.
Scala util.
Scala util. Thank you very much. Okay, so ladies and gentlemen, let's try doing this. Import scala.util.underbar. This is like saying import everything in Scala utilities, okay? And what we will say here is that we're going to create now a try value out of a value 3, okay? We're just going to try evaluating 3, but we're going to do it in a protected context where, regardless of whether it succeeds or fails, it gets a nice value. So try of 3 is just a value. This is a monad, it turns out. Success of 3. Okay, now watch this. Try of 3 divided by 0. Now this is also a try, but you notice it doesn't, if I just do 3 divided by 0 like this, what do you think will happen? Yeah, an exception will be thrown, ladies and gentlemen. But you notice that exception is not thrown here. Instead, I get back a value. So I could say, value my bad. 3 divided by 0, right? Here we go. And this is actually a value, and it's a perfectly good value. I can actually say, my good, right? My good would be try of 3. Now, watch this. This is the really fun thing about this. Oops, my good. Okay, val my good. Sorry, val my good. Okay, here we go. I could say within this context, my good dot map. I'm going to square this. Boom. By the way, this is a function. I'm passing it a function. Passing a function that takes an argument and it squares it. So I say, for whatever you have in you, square it, right? This is passing the squaring function, yeah? So whatever inside you, square it. That's what we did with stream, right? That's what we did with stream up there, right? We mapped it with this. Same thing here. What do you think will happen if I do it with my bad? What do you think will happen?
Through exception?
No, it turns out that it propagates. So all it does is it gives me back a value, which encapsulates the value, the failure. So regardless of whether this gave a good or bad result, I can treat it like a full value. If it's a bad value and I do an operation, I'll get a bad value out, a distinguished value that indicates that what the problem was. You notice it's still indicating the nature of the original problem, right? On the other hand, if I have a good value and I do the operation, I'll get a good value out that has the answer in it. And this allows me to have, in the middle of a pipeline, a complex pipeline, an error that goes wrong, and it will carry information about the error later, but it doesn't break the pipeline. It doesn't bust out of there and say, I need help, I have an exception, and force you to have to somehow go and resume it later. It's still in the pipeline. It just gets processed along. I mean, I can even do something like this, filter things that are less than 0 or something like that. Oops. Well, okay, I'll show you a shorthand. So it turns out that I could say this, but if I have something as simple as that, I'm creating a function, it takes a single argument, and then it refers to, I can just use this. It just doesn't name it, okay? And that gives me a value as well, okay? That captured that original value. So this is an anonymous function. This is the same as saying a function that takes some argument called, say, x, and it tests if x is less than or equal to 0. It just doesn't bother naming it. Whatever the name of the argument is, it implies there's one argument. Whatever the name of that argument is, test if it's less than 0. Less than or equal to 0. Okay? Yeah, can.
What it returns is a function or is it actually just
No, it's a value.
It's a value.
No.
And that it is a value, say any operation.
Well, I'm sorry. Yes, it's a value.
Yeah.
It's, in this case, it's a wrapped value. So think about it it's a try. It's returned a try. Because this my bad is a try expression. My good is a try too. My bad is a try. And when I apply a map to a try, I get back something else that's a try. And when I apply a filter on a try, I get back something else that's a try. Just like if I had a stream and I applied a map on a stream, I'd get a stream. If I applied a filter on a stream, I'd get a stream.
It's a type of try.
Yeah, it's a type of try. Yeah, this is a type of try. By the way, same thing occurs to arrays here. So I could do val my array equals, sorry, I'm not that creative today. It's better than foo, maybe. 1, 57, 53 minus 10, 30, 4, right? Here we go. And you notice it knows that it's an array event. It has type inference. This is awesome. So it's strictly typed, but it can infer what the type is. Those are a bunch of ints. It knows it's in it. Okay, now watch this. My array dot map. Let's square them all. Right? What do you think I'll get back? I have an array. I'm mapping an array. What will I get back?
On stream,
I'll get back an array.
right?
An array. If it was a stream and I was squaring that, it applied map to square each element of that, it'd get back a stream, but here it's an array. And then I could, say filter this thing less than or equal to 0. Filter all things less than or equal to 0. And I'd get back, guess what? I'd get back an array, it turns out. So an array consisting of 0. I suppose I were to do it the other way, just so you could see this. I'm going to filter all things greater than 0. What will I get back? An array of those things.
I have a
Question?
So when we apply this map function on my array, do we change the value of my array or
No.
just create a new one?
No, new array. No.
Because array is a mutable one, right?
No, array buffer is mutable. Array is mutable only in the sense that it can be extended.
Okay.
Yeah. There's we'll discuss that at length in Scala, and I may be wrong. I've got to double check my memory with that, but there's array buffer and there's an array, and each of them have differences. And then there's a thing called a vector, which is actually more common than array. It's strictly read-only in a fixed length. Okay, and we'll go through and discuss that type hierarchy soon enough. Okay, but yeah, since we're mapping a collection, we get back that same type of collection. Okay, Scala has a whole swag of collections. It has vectors, it has arrays, it has dictionaries, it has and maps, it has a whole bunch. Okay,
Is tuples kind of collection?
sorry.
Tuple?
Tuple, yeah, a collection, a tuple. Oh, they're awesome.
I don't know why.
Sorry? Yeah. But a tuple is written like this, and a tuple is different than a vector in the sense that it can contain different types of things. Yeah, and what's really awesome is you can have this on the left-hand side too of a statement. So you could say like you could have, I don't know here. You could define a function, for example, which returns a tuple and just assign the tuple to the return value of the function. But you could do it in a named way. That's awesome. Okay, you got to see this, but time is short. I can't do it right now. Let's just talk about a few more so we can finish up here. It has clear dependencies. What depends on what? It has really nice way to specify asynchronous operations. So you can pass around these things called futures. A future, like you could think of a stream as like a promise of a computation. It will do the computation for you when you need it. It knows how to do it. As soon as you request it, it'll compute it. But it won't compute it unless you need it. A future is a promise of a value. It'll get you the value eventually, but it may not be done yet. And you can pass it around. It's just a value. But it's a value that still might not be computed. Okay, so we have futures, which are very nice for doing asynchronous operations. Whenever it's done, it'll be available. And you can say, when this is done, do this, and you can chain them together. When this is complete, do this. When that's complete, do this. When that's complete, and get an entire thing. Potential for pipelining, I say less clear to practical. No, it's actually very practical. I'm gonna delete that. It's actually very, very clear. So you can create these pipelines in very nice ways. You could send code to different machines with minimal trouble using functional programming because each can recompute or reuse existing operations. Immutability, it turns out, rules out many common errors that we encounter in object-oriented or imperative programming. And the fact that we can do these maps, we can do these filters, we can do these reduces, etc., it turns out that that allows them to be done in a very easy way in a parallelized fashion. Okay, you could say mapping, right? That mapping we did earlier, mapping of an array, right? This mapping of an array thing here, that array could have had 1 million elements in it, and if we want to do a map of squaring the array, we could break that. Let's suppose it has 1 billion elements. And that's not an exaggeration for some of the sizes of data we'll be handling in future months. We may press up against that, like with Ethica data from large studies and accelerometry. So if we have an array of 1 billion elements, we don't want to do it on just your computer. We want to have it run on machines out there. If we could break it up so many cores could work on it simultaneously, each of them can just apply this operation, square. As long as they have the data, they can square each element of their operation independent of this next one, independent of the next one. They could filter in common, right? The first one will take the first 1 million elements, the next million, the next million, and we'll each look for this thing within that million. Through additional mechanisms, they can do at least a more intelligent form of reduction, reduction to a single value, say. And it turns out that there's a kind of natural match to analysis workflows. Okay, we're going to be talking about Spark. It turns out Spark is a platform for distributed cluster computing for data science as a key need. It's a general platform, and it really emphasizes performance, including interactive exploration, doing exploration in an interactive fashion. It provides this sort of common stack for doing this, where you can mix and match mechanisms across different pipelines, and you can you can work on sort of updating one system, in this case Spark, rather than dealing with all these incompatible different systems. So Spark is kind of a unified platform for doing doing data science interactively or at larger scale in a routine way. It supports cross languages. We're going to be using Scala interface, but it also has PySpark support, and I think it's particularly with the Shiny interface, it has RSpark support. There's support for R. And it interfaces with a lot of other key leading technologies, Cassandra, Hadoop, SQL databases, as well as things like Flink, Flume, Zeppelin, Kibana, etc. It has multiple components. We'll be talking about ML. We'll be talking about Spark Streaming and Spark SQL particularly much. Some might be interested in GraphX. And it's evolving very rapidly. Between the last time I taught this course and now, it's evolved quite a bit. Okay, not unrecognizably by any means, but quite a lot. There's some things that have changed about how you do things, etc. Key performance advantages because of distributed computation, because of memory-conscious computation. We could do a lot of computations in memory for iterative algorithms rather than hitting disk. And it supports lazy evaluation, immutable data structures, and user specification and memory constraints. And this is my final slide. We'll see coming up in this context immutability, recording of provenance, how this was calculated, the lineage of a given value, where it came from. Why? Well, among other things, it can be thrown away and recomputed. If we don't have time to keep it around, just recompute it later. Materialize it when we need it. It supports this concept of resilient distributed data sets and derivatives called data frames, data sets, which are types, the left being a type-safe version, that are even more functional. But resilient distributed data sets allows us to do these operations over massive numbers of machines in parallel. it supports laziness, and has the same distinction about when we only compute something when we need it. Okay, and because of that, we can be very memory sipping, only use small amounts of memory. And it also allows us to have quite a bit of control over distributed processing of data by use of partition, careful management of partitions, and shuffling that goes on between data. There's implicit conversions that occur before data types, which mean that even though it's type safe, it's very convenient, much more convenient to use than you might think for some things. And it does support type safety computation and this notion of data frames, which is quite similar to what we see in other areas like R, for those who have used it, or in the Python context. When we're manipulating data, we have tabular data with multiple columns and multiple rows. We can use these things called data frames to do the manipulations in very natural ways. Okay, so we'll be delving into this more next time, and we'll finish up here. Thank you for your patience while we dealt with the AV issues. We'll be sure to have a VGA cable not borrowed from a student next time, and see if we can avoid similar dysfunction. Okay, thank you very much. And I'm going to give you a little bit of take-home exercises to do by next time to explore a little bit more some of the things we did this time. Okay? Thanks very much.